run a little long in that last segment, so I don't know if I'll be able to get us back on track, but a lot of the things I'm going to discuss here we've talked about before, so some of these slides we might zip through pretty quickly. Anyway, but I want to talk today about stealth antennas. Stealth meaning covert, low profile, or not easily recognizable. And why do we need a stealth antenna in the first place? I mean, oftentimes many people run into this particular situation of which I am one. You got constraints. These days, houses are built on smaller lots, HOAs, covenants, those types of things. Restricted lot size, we got all kinds of things that work against putting up a full-size antenna. And so, faced with this dilemma, you've got a small space, but you need some kind of hopefully a big antenna performance. So how do you go about addressing that? Okay, so the challenge is, how do you make it perform in a small space? And the other thing that happens is a smaller antenna, a shorter antenna, that will fit in an available space. We'll see subsequently in here that you don't have as much gain. It can be compromised in that way. And we'll talk a little bit about how to make a stealth antenna. Maybe don't look at it for that. And then maybe some ways of hiding it. So the other thing you got to be concerned about is operating issues. And the performance of a short antenna, as you can see there, lower gain, the less wire you have in the sky, the less pickup you have. There's so much energy in a passing wave. You have a small collector for that. The smaller the energy you're going to collect, and then it shows up as lower gain or lower sensitivity. And typically, if it's a compromised antenna in this way, if it's shorter, it's going to be a narrower bandwidth. We talked about that a little earlier. And so there'd be some sort of tuning element or operation required. The other thing is that if you have a compromised antenna and you're hiding it somewhere in your house or your attic, you're now likely to be in closer proximity to things that can induce interference into your antenna system. So you could end up with telephone, PC wiring in the house, that kind of equipment. The other thing is that with these kinds of antennas, because they're maybe in closer proximity to yourself, or your operating thing, because it's in your house or above your house, say in the attic, you're probably going to be running no more than 100 watts. You're going to be doing 2-hour power, typically on one of these things. And then safety is another thing. The fact that some people even put the antenna in the same room where they're operating in an apartment or some situation like that, then you've got to make sure that you're aware of the RF exposure. And then, of course, structural integrity. We talked about that earlier. So some of the things you need to think about is the RF transparency of wherever you're going to mount your antenna. So if you've got a wood frame house and you happen to be putting it somewhere in the house or in the attic, the transparency of that is actually good. You don't have much trouble with transmitting and receiving through those kinds of medium. But you do have to be aware of internal conductors such as house wiring, ductwork, that kind of thing you might be in close proximity with. That could actually form antennas which be more absorptive type of phenomena than reflective. And this is also the wiring, power wiring, so forth and so on. Even copper plumbing could be an issue. And then, of course, and like was mentioned earlier, if you have a stuccoed house and there's chicken wire and that, then obviously you've got a Faraday cage around the lower part of the house, but hopefully the roof of the attic or the eaves outside or whatever would be free from that. And then concrete structures, of course, that's much worse because they're likely to have the rebar built in and metal frame windows and things like that that could be absorbed and affect your antenna. So we've already talked a lot about theory, but as I said earlier, there's only basically two forms. There's a dipole, which is typically the horizontal mode, and the vertical form, the vertical mode. And then we'll talk a little bit about short antennas, properties, behavior, performance. And what might be best depends on your particular circumstance. So I won't go through this. I mean, this is a very basic picture. You got a transmitter, you got coax speed line, and your antenna is basically a resistor. And that resistance is composed of your resistive losses, which is heat, and then what's is called the radiation resistance. That's where your power is actually, most of your power that you want is dissipated in the radiation resistance, which is your propagated signal. And then we could talk about the standard antenna, which was mentioned earlier. This is a resonant half-wave dipole. And I believe that the resonant one is a half-wave of a wavelength elevation above ground, 50 ohms at resonance, no VSWR, maximum power transfer, all those kinds of things, which is ideal antenna. So the short antenna properties, again, the gain is reduced due to shortness. I mentioned that. Feed point impedance changes. That means that for a shorter antenna and what we can say here, as you sweep across the frequency band, it may be tuned to a specific frequency, that the impedance will change, obviously, if it goes out of resonance. So an antenna that's no longer resonant at the desired frequency, radiation resistance drops, capacitive reactance appears at the feed point, and you can end up with a high VSWR. And then, of course, as the efficiency drops, the ohmic losses become a lot more significant part of the feed point impedance. So there are some solutions here, but again, we're sticking with what are the basic antenna forms. Dipole. We talk about loops. We'll talk about it in a lot more depth in a few minutes. Then there's the verticals and wires like Greg was just talking about. Those are all types of forms of antennas that you might have that are trying to shorten or hide. So the first thing that has to happen is if you take a dipole and you shorten it, so it'll fit in some particular area, it will begin to look capacitive, and it's no longer resonant. So you need to restore the feed point impedance so that you get back up to a 50 ohm, hopefully pure resistive load. So there's a couple of ways you can do this. One of them is putting a trap or an inductance somewhere in the antenna. And that basically what it does is it nulls out the capacitive effects. So what you've done by putting an inductive trap in the antenna is you restore it back to resonance once again. And you can do this both with dipoles as well as vertical antennas. And a lot of times what they do with verticals is you can put a capacitive hat on the end of the antenna, which will actually make it look longer. Okay, so first we'll talk about a coil-loaded dipole. So it's a balanced system, just like a regular dipole. Typically they're single band. We can talk about that, but there are configurations where you can put multiple traps in a dipole and make it multi-band. There's ground issues there because the dipole itself, it has both elements of the antenna included. There were some examples here of how you might shorten a dipole. For an 80 meter one, you can go from 132 maybe down to 69 feet. still pretty long, but that might be a difference, that could be made on a particular lot size, so we could accommodate that. 40-meter dipole, you can get down to 38 feet perhaps. And it's most likely an outdoor application because most people don't have attics like that big. And the tuner, the radial tuner should be okay. So if you're a little bit off on your SWR, the limited amount of tuning that typically found in a modern transceiver should be adequate for bringing that into resonance. So loading coils, they're inserted in series with the antenna to make up for the shortness. This set counts as a capacitive component, resonates the antenna, and then for dipoles you put one in each leg and one out towards the bottom. So it might look something like this. As you can see, those are, it's actually some PVC. Those are just wrapped in some yellow copper wire to make up the inductance. There are design equations and things you can find online that help you if you want to design your own, or leave available commercially. And that is typically what they look like when they're inserted in the dipole, one in each leg. The other thing you can do is, we talked a little bit about external tuners. What they do is they don't actually bring the antenna back into resonance with the short antenna. It says that there's no inductive or capacitive loading that's actually added into the antenna to make it resonant. What it does is it matches the complex antenna feed point impedance, and then we've got whatever the resistive component is, plus something reactive, inductive or capacitive, and it basically compensates for that. It sort of tunes it out. So the antenna really is not resonant, but it's from the transmitter side, it looks resonant. It looks like it's just a straight fit deal. And those are useful for multi-band operation. And there may be tuning limitations if the tuner cannot match the antenna with the feed line impedance. Again, it's not brought back into resonance, and like I said, brick tuners are not well suited for off-resonant antennas because they usually don't have the range required to bring it into to make the transmitter happen. Now this shows a kind of a random link to the any link copper wires, the dipole configuration, as you can see. And in this case, they use a 450 ohm ladder line because it's low loss. And then you got the antenna tuner down here at the bottom of the ladder line, and then you got the coax to your radio. I've got one of these in my attic. It's got the 20 meters, and I have an ATU, and it's mounted right here. And so the coax just goes right up to the ATU. It works great. I mean, it's pretty naturally resonant at 20 meters, but when you go to lower bands, it starts kicking in a lot of inductance and capacitance. And one of the biggest drawbacks is for the lower frequencies, it's not at an ideal height. And the attic is probably no more than about 15 or 18 feet off the outside ground level. So it's a low elevation dipole. And we've seen the effects of that in the radiation pattern. It's that low, a lot of the energy is going straight up. So there are some different ways you can go about doing the stealth antenna. I don't know if you've heard about these things, the flagpole verticals. Got a picture of one in a second. These are ground mounted. They're HOA friendly because the federal government has said that you can't stop anybody from putting up a flag on their property. So, inventive hams have come up with antennas built into flagpoles. So some guys will lay the wires on the rooftops if you have composite shingles. Sometimes you can get away with that on the apex of your roof. It's just talk about types of wire that's good to use there. Wires on gable ends. Those aren't good if you've got aluminum eaves or aluminum gutters, obviously. That would not work. Some people go low, mounting very low elevation on fences. If you have enough fence length around your property. Some people have built loops onto those. Again, a lot of this information, you start looking online and we get inundated with all kinds of ideas. So there's a lot of stuff out there that you can do. I haven't seen a Yagi in an antenna in an attic, but I guess it can be done because you have enough room. And again, if you're talking higher frequencies, that's a lot easier, like what Bob was talking about earlier. There's a lot of different types of small antennas that work well, but you go inside your attic. And there are some that might look like a TV antenna that was discussed. And they have this one like an antenna that looks kind of like a jet pipe. Those are out there. This is an example of a shortened vertical. This is a QRP guy's antenna. This is a 40-10 shortened antenna. It's only 52 inches high, but it does require radios or counterpoints to function. And that could be, either a portable antenna or you possibly could hide that fairly easily, especially if you have trees in your yard, or some way that you might disguise it or hide behind something in a way that it's not very visible. But the fact that it's only 52 inches high would make it attractive because that's not very visible from the street or somebody else's yard. This is off-center fed. Vertical is built into a flagpole. Obviously, probably typically what they do is they run a wire up inside that, and it would be like a non-conductive material, like carbon fiber or fiberglass. If it was metal, they would have to actually use the pole. And it appears to have a tuner, something right there that couples into it. This is a buddy pole. That buddy pole makes a lot of different antennas. There's a small and more compact. This is one of theirs that I just found a diagram online. But that's just rather small, and this one actually works down to 80 meters. So, kind of at the bottom of my presentation on the stealth. This publication here, ARRL, small antennas for small spaces. This is the gold mine information. And it's a free file. If you go online and you just Google for that title, you'll find several places where you can download it as a PDF file. So you get a free book out of that with lots of information on how you might go about building a small antenna for whatever small space you might be restricted to. So they have all kinds of different versions of compact antennas included in that. So the next thing I wanted to talk about, which I have to make things more near and dear to my heart, is a magnetic loop antenna. That's what I've got here. Let me pull this over. Not to see why. So these are somewhat. These operate somewhat differently than what we've been talking about before. What you see there is one like this. It's not the same antenna, but at my home, I just basically hang it under an elevated deck that's above. So they work well low to the ground. And this particular one is a 20 through 10 meter continuously tunable magnetic loop antenna. And we'll go a little bit through this. I'm trying to go quickly, but we're talking about what exactly it is. It's we call it a magnetic loop, or sometimes they call it a small transmitting loop. You can see it by both names. There are differences between a dipole and a loop, and we'll talk about that. And why does it make a good stealth antenna, and a little bit about how you can go about constructing one. One of the beauties is that you can build one of these things out of some very commonly available materials pretty easily and not require a lot of sophisticated tools or anything like that. So basically what a magnetic loop antenna is you've got coax feed line, and then it feeds into a small primary coupling loop, and then there's a larger outer loop with a capacitor at the top. And what this combination actually is this business right here. It's actually a transformer. So this is actually the small loop. That multi-turn thing is actually just a single turn that's much larger. And then there's a variable capacitor. And the way this thing transforms from 50 ohms to the very, very low radiation resistance that happens to be the property of the large loop is by the physical difference in their circumferences. So if it's like if this is a 20% circumference of the larger loop, it'll come in to be about 50 ohms. So that size difference is what does the turns ratio basically. A magnetic loop is typically about 1/10 of a wavelength. If it's going to be a true magnetic loop. If it gets larger compared to the wavelength, some of the properties change and will still resonate, but the radiation pattern begins to shift. That's like what Greg was talking about with some of those antennas he discussed. So the radiation pattern is much like a dipole. And so this thing is usually compared to a dipole when it's oriented like this. In this mode, it has a horizontal radiation pattern. It works low to the ground. If you put it horizontal, it'll have a vertical type radiation pattern, but it needs to be high in the air, much like a dipole to work properly. So, you saw this earlier. What you see here is, what I want to do is just kind of compare the dipole with the loop. The dipole works off of the E field. Okay, that's the red here. And this is our pointing vector, propagation director. And then the blue represents the magnetic wave. So, as we said earlier, electromagnetic wave has both components. Typical dipole type antennas use the E field to excite them or transmit the strong E field. This little guy works with the magnetic field. So both components are there in a radio wave. And what happens is when a magnetic wave passes in this direction through there, the fields of the magnetic portion of it excite this loop, the larger loop. So there's currents induced into it, and because it has a capacitor and an inductor, it's a tuned circuit, it's a resonant circuit. So now you get circulating current running in the antenna. And if it's in the receive mode, obviously that the weaker signal now is exciting the larger loop. Magnetically, it couples into the little loop and the coax takes it into your receiver. Conversely, when you transmit, you feed power into the little loop, it magnetically couples to the large loop. It begins to circulate large currents, and basically what happens is, because of that, the phenomenon of propagation takes place. Energy leaves the antenna, and I guess the way to think about it is that this loop is loosely coupled with whatever the receiver is out there. So you're basically coupling the magnetic fields that are generated by this into an antenna somewhere in a distance that you're communicating with. Okay, so this thing is made up of this capacitance. There's a distributed capacitance that is just a natural part of something large, and whenever you put a wire or anything into space, you get a distributed capacitance. Key here is you've got two things that are dissipating your power. You've got radiation resistance and you have a loss resistance. We talked about both of those earlier. And this guy is obviously you got copper. It's going to have some finite losses, and the capacitor itself can lose energy if it has a high ESR, that kind of thing that happens. So you really want this to be very, very small compared to this, so that you get maximum efficiency. Okay, let's look at the radiation pattern. You've seen this figure before, but here's the loop here, and we're looking down on it. And as you can see, it has, looking at this one where the red represents the strongest part of the magnetic field, blue the weakest. You can see that it's kind of a donut shape, and you sort of see it here with these two main lobes. And an interesting thing is here is that you get, these are the various elevation takeoff angles that this antenna provides. So it does have a lot of energy at a lower takeoff angles, but fairly uniform. And you can kind of see here, you get fairly strong propagation out at multiple elevation angles. So it works well for close in and distant type of communications. So real quick, differences between a dipole and a loop. Typically a dipole is half wavelength long versus something as small as 3 feet. As you see here, it's in the, with a dipole, you need to be about a half wavelength or so or more above ground to get your ideal takeoff angles and radiation patterns. This thing only needs to be about 1 loop diameter off of the ground. And the reason is because it generates a strong magnetic field, but for the earth underneath it, there's not a strong coupling into the magnetic, or the magnetic field won't connect strongly with the earth. So it can actually operate very close to the ground. Unless you put traps or do some other things, you know, a dipole is typically single banded. This can be multi-banded because it has a tuning capacitor that lets it cover wide frequency ranges. Quarter wave vertical requires some sort of a grounding structure underneath it or counterpoise. This has no dependency on the ground system. Typically you need to elevate your dipole, and within a dipole, compared to this thing, the voltages and the currents are much lower for a given power level. For this thing, you'll see, they can both be very high. It's a high Q antenna, so when you feed energy into it, it develops very large currents. That's why you need a fairly wide or large conducting material for the large loop. This could be up in at 100 watts. This could be something around 18 to 20 amps of current flowing through there, and several kilovolts at the capacitor plates. So that's one of the things you got to be aware of, is if you're running high power, those are safety issues that could be a factor. Of course, comparatively, a dipole would be a lot broader band and efficient compared to this guy. He's narrow band and he's less efficient, and that's because there are finite milliohm losses within the structure of this thing. But when you have a radiation resistance that's in milliohms, the loss resistance becomes significant. So you've got to be aware of that. And then, this here is I just said that a dipole is really cheap to buy or build because it's just basically a wire antenna, not a lot to them. And these little guys, they aren't available commercially. They can be quite expensive to buy off from a vendor, but if you build your own, you can do it very reasonably. So why is it a good stealth antenna? Well, obviously it's small, and so it's pretty easily disguised. It can probably be disguised as yard art if somebody complained. But the fact that you can stash it most anywhere, or it's very portable. I mean, like in this configuration, it's pretty easy just to take it out and set it in the yard, use it, and I'm done, bring it back up on the porch, type thing. So there's no ground plane required. To be mounted close physically to the ground. Again, one diameter or diameter and a half up is high enough. It can go higher, obviously. Like you say, it takes away friendly due to the small size, and you can hide it easily. And you can also put one of these in the attic, which I've done. I won't talk about that. It could be a covert outdoor antenna or a portable even indoor antenna. I know a lot of guys that I've seen online that will have a version of this operating in the same room with their radios, but typically QRP powered because you don't want to run a lot of energy when you're right next to it. And they also make a claim that they're a lower noise antenna. And part of the reason for that is the fact that they're very narrow band. They would be less atmospheric noise that would be sensitive to. And the other thing is that it's more sensitive to the magnetic field. And some of the types of noise that it could help null out. And again, it does have nulls in the broadside that might orient it towards wherever the noise source is to help null that out. The fact that if it's an electromagnetic field noise generator, it'll have a magnetic component, obviously, because it's radiating. But if it's something nearby in the near field, then you may have a stronger E field than a magnetic field. So it could be a lower noise situation, depending upon what your particular problem might be. So, one thing I did a couple of weeks ago, I set this out in the backyard. Obviously, when we talk about antennas, all of this has been theoretical, so I wanted to show a real-world sort of a response. So I set this in the backyard. I set my transceiver for 5 watts, and I used the whisper mode. I'm not sure if you're familiar with that, but there's a weak signal propagation reporter app online. So if you transmit a whisper signal, you can get a report of who all's hearing it. And so in this particular case, I was running 5 watts. This is about 3 o'clock in the afternoon, so the 20-meter band was fairly active. But you can see a couple of things here. One is you can kind of pick out the figure 8 pattern here. So you see the lobes are more east-west because that's the orientation of the antenna. And it did reach some pretty good distance. I hit in Hawaii, one here in Scotland, Germany, Austria, and Canary Islands. So it does work. Again, it was just as you see it right now, 10 to 5 watts. And you can scale these things. So the other thing that could be done, this antenna could feasibly work at 40 meters. However, the efficiency would drop way down, and you need a four times the size of the capacitor and capacitance here in order to resonate it at 40 meters. So the way I got around that was I just made it bigger. This has got twice the circumference. So it's a 6-foot diameter one, but it's in the attic, so it's in a stagnant airspace. And on this particular antenna, I did the same kind of a test. And this was in the evening, obviously when 40 meters was alive. And it was a whisper test. And again, you can see the figure 8, so the response. But it worked well. Now that, I guess the key point there is that's a 40-meter antenna that's operating with its center of the antenna is about 18 feet off the ground. So it's a real, very low altitude, the elevation, I guess, for a 40-meter antenna. Some of the commercial ones that are out there, these are MFJ, we talked about them, they have all kinds of ham radio equipment. They do make magnetic loops, but you can see they're a little pricey. They're $600–700 range for theirs. They use aluminum tubing for the main loop. One side has a butterfly type variable capacitor, and then a feed loop on the other side. And then for QRP, Chameleon is another source for loop antennas. I just put this one up here. This is one that's manually tuned here, where the previous one has these controllers. Because you have to have some mechanism for tuning your capacitor remotely if you're going to be able to cover the bands. So these come with these controllers. The Chameleon, this particular one, has a manual, just a knob there, so you have to tune it manually. These are typically used for field work, or if it's in your house, or on an apartment balcony, that kind of application. So, just real quick, I'll go through this because I'm almost out of my time. if you wanted to build your own, okay, some of the things you need to think about is you need a low ESR capacitor. You can't use like the standard broadcast tuning capacitors for this, because it has wiper contacts that usually makes up too many milliohms and resistive loss. And it will kill the efficiency. And also the capacitor, if you're going to run any kind of power, it's got to have kilovolt ratings on it and high amperage capabilities. You can use just about anything for the main conductor. I happen to use copper ribbon for this one because I wanted it to be portable, and this is easily to take apart, and because it's all flexible, you can just roll up the copper ribbon, make the whole thing pretty small for transporting it. But you can use like copper pipe. People use semi-rigid coax, like we saw some earlier, that sort of thing, like heliac. You want to minimize the number of solder joints, and if you do have them, we recommend using silver solder to minimize any resistive losses. The shape can be, it's not critical, circular, octagon, square. Circular is the most efficient because the more area you can enclose, the more efficient the antenna will be. And like I said, you need to minimize every milliohm of resistance, because that represents loss. So what kind of the gold standard for a tuning capacitor is one of these guys. It's a vacuum variable. Most of the ones that the guys use, they buy off eBay, and they come out of the Soviet Union. They're kind of, well, Russia, I should say. They're Soviet era devices, and people sell them surplus, but they're expensive. It could be a couple $100 for one of these. They're big, they're heavy, and they're fragile. But they're very efficient because it's in a vacuum, and they have a wide tuning range. It uses a bellows here as the ability to pull this part of the thing in and out of a set of concentric rings that it interfaces with. And that's how it tunes. You turn this shaft where it operates that. Or, the old standard type capacitor, variable capacitor would typically be a transmitting type. These are usually found on flea markets or surplus somewhere, if you go that route. The feeder loop can be done a number of ways. I just threw this in here because some guys will go with using coax to put a Faraday shield around it. If they might be prone to some kind of electrostatic interference that the small loop picks up, you can shield it and still have it work magnetically for that part of it. This one uses just a standard house wire, just to make a loop to feed it. So this is an encouragement. These are just how I built mine. A lot of this stuff is readily available. You can make it out of 3/4 inch copper pipe. This is Home Depot, Lowe's. I used 135-degree elbows to make your angles and solder the solder joints together. This one's made out of a strip of a copper sheet, I should say. It's been cut into strips and then soldered together. The frame of the thing is made out of a stir stick. This little guy is a 632 threaded shaft, which allows this thing to tune, which means this plate goes up and down. That tunes the capacitor. The ribs on this wheel-shaped frame is just these little snow markers. Those are Home Depot. I bought some extruded aluminum angle bracket to make some of the parts. I used blank PCBs for up here to build the capacitor. And then there's some aluminum plates that are used for the tuning part of it, which would be as you call these, the stabbers, and just like the rotor for the conventional capacitor. And those are Hobby Lobby or Ace. And then just some 632 hardware. The other thing is, just real quick, is in order to design one, they say you can go online and find calculators. This one is pretty useful, 66 Pacific and you can just put in what you want to put for circumference for your antenna. You can say what sort of pipe you're using, or whatever that material might be, the frequency you want to operate, and the power level that you want to operate. And then it'll give you a readout. So it'll tell you the efficiency, ideally, the bandwidth, tell you how much tuning capacitance you need, tells you what the voltage peaks are. This is RMS, so this is not even peak voltage, but you're over 4 kV there, RMS, 18.8 amps of current. Radiation resistance is only 100 milliohms. So you're obviously working with very small resistance there. So that's where there's loss resistance, you want to keep that as small as possible. In this case, it says it would predict it to be about 40 milliohms. Inductance, 2.5 microhenries. And that's what this is. I measured this thing when I built it, and it was 2.5, just like it said. And it gives you some other things. But there's also another factor, it's the distributed capacitance. That'll enter into, because it's actually in parallel with the main tuning capacitor. Something to consider. And then there, same calculator, you just pick a different part, and you can design your tuning capacity. Just give you the size of the plates, the area, the space, number of plates, using air for a dielectric, and it'll tell you what you get. So in this case, this is 110 picofarads, which is what this guy is. But there's two of them, there's one here, and they're connected in series by the movable plates. So you get half the capacitance, but twice the voltage rating. And that way there's no rubbing contacts, there's nothing more than soldered contacts, and the sliding plate connects the two capacitors. So here is nano VNA showing what the actual bandwidths are, and this is the response here. This is being swept from 13.8 to 14.5 megahertz, 20 meter band. 1.16 is the VSWR, but you can see how narrow the band is. You get up into a couple of 2.3 dB, I think, is where you would tell you your typical bandwidth, those 2 points. It's pretty narrow. So you can actually peak this up and get this to have a much closer to 1-to-1 VSWR by adjusting the actual circumference of the feeder loop. So I didn't get it exactly right there, but it's very close. And then what happens is, as you go higher in frequency, you can see the bandwidth gets a little wider. This is a little different sweep pattern, but or range. But you can see it's getting wider, and we're beginning to lose the VSWR. And you can see it gets wider here on 15 meters, and then this is 10 meters here. And the reason the VSWR is getting affected is because the radiation resistance is going up. As the frequency goes higher radiation resistance, and I'm still tuned for that turns ratio at 20 meters. So, but these are typically small enough that you could, once it's resonant, you could use the tuner and transceiver to actually know that out, get a little VSWR to define this. And then this is just the final one here. This is what it might look on your radio. This is my 40 meter one on the 7300. This is an attic mounted dipole. You can see it's pretty flat. That only goes across like 130 kilohertz. It's pretty flat, but you can see here on with the loop antenna how quickly it drops down, or how quickly the VSWR goes up as you get off frequency. So you got to pay real close attention to the tuning of this antenna. So I just wanted to give a couple of references here. Blackstone Valley Amateur Radio Club, they put together a lot of the stuff that the first part of this presentation on stealth antennas that I borrowed from them. I want to give them credit. And then I would also recommend this. And this is a paper that was written by this guy, Leigh Turner. He was kind of the guru of magnetic loops. He just died recently in the last couple of weeks, which is a sad loss in the community. But you can find his work online as a downloadable PDF. But he goes into a whole lot of information in detail on magnetic loop antennas. And just, I put a little final thing in here because I did another 40-meter listen the other night, and I got a surprise. I saw this one that went out to Hawaii. I said, what is this guy? And it turned out, he's hitting the research station in Antarctica. I mean, come on. And I went and looked, it's a little blurry because I didn't do it right when I did the screen capture. But I looked it up on QRZ, and it's a German research station called Dumeier 3. They talk a little bit about who they are, but they have a radio station there. Ham operators use that a lot. So, any questions?
What's the blue light?
Oh, the splashing here?
Yeah.
Okay, what I didn't go into in a lot of detail, because it adds complexity, I really wanted to talk about just the theory of the antenna, but in order to tune it, you've got to be able to have a pretty fine control of running this plate up and down. So this is a 632 threaded shaft, and inside here is a little stepper motor that turns it, and then there's some electronics that go with it. That blue light comes on when the thing activates, when it powers up, and I've got it's got a circuit in there that kind of discriminates a certain signal that comes from the controller that when it sees that, it will power the thing up. But it's not perfect, and so when we get interference, it hits it and it actually turns on the power, but it only stays on for 1 second and then it shuts off. But if I was to just do something real quick, like I was going to send it a signal and make it move.
Cool.
See it move a little bit there.
Yeah.
Make it move a lot. This would be like 17 meters. It comes down, and then the controller is set up so that it's calibrated, so I can just program in a frequency, and then when I activate it, it'll tune to that point.
Did you make that, or is it commercially made?
No, it's all home. Okay. Yeah.
This is
Invested in
Pardon me?
how much do you have invested in your
In time or money? Time a lot. Not tons of money. I use little Arduino Nano clones. At the time I bought these, they were like $3 a piece. The circuitry is pretty simple. I've got schematics if anybody wants to see them. But, dollar-wise, this thing is probably $75.
I've seen them very expensive on the internet, and HRL had one for like almost $2,000.
Oh, yeah.
The Italian
Yeah,
guy.
there are some out there that are very pricey. So, this I designed for 100 watts. And a lot of it has to do with the air gap in the plates. Is it what? Yeah, because I can key it with CW and just leave it there. I published actually on magneticgroups.io. I put a paper out there to describe not this particular antenna. It's very similar, and it has how to build it, and it has parts list and a full description of both the transmitter, receiver, and the code. It's called magnetic loops or magnetic loops. I think it's a user group, and it's at groups.io.
So what did you use for your capacitor? You showed us a photo of those Russian.
Yeah, so this capacitor is made up of this is a printed circuit board up here, and on the other side I got it. There's like about a 1/4 inch gap cut in it. So here you can see this part of the copper band come up. It split, comes down. This little piece here goes on the inside and soldered to the inside of the copper plate, and one on this side. And there's the same thing on the back side. And so that makes two fixed plates here and two fixed plates here. And then this guy, this part of it, when it runs up in there, that makes this capacitor. And when this part goes up in here, it makes this capacitor, and they're connected together because that's a common plate. So, anyway, you're all welcome to come look at it. Oh, I'm sorry, another question. And even after we're done, come in and we'll talk, because we're getting way off time here, so, but go ahead.
That whisper chart, is that like an automated signal recording system?
Yeah, all you do is do a transmission, then you go to whispernet.org online, and then it'll bring up a map, and you can put in your call sign and the frequency that you're operating on. And then after you've done the transmission, it'll show you all the hints. I mean, there's other things you can use. There's whispernet.org, there's PSK recorder, there's reverse beacon network. There's all kinds of things you can do to look at your propagation.
Thank you, Jay.
Okay, guys.